Hello everyone, in this video we're going to solve exercise 6 for the topic of first order systems. So for the differential equation given, we want to find the steady state response, as well as we want to determine how long it would take to reach 98% of the steady state response. So the first step is to take a Laplace transform, rearrange it, and then we can use the final value theorem to find the steady state. So for our function, we have 2s xs minus x naught. I mean, it's 0 here, but we need to incorporate it. Xs equals 10, and then we have a unit step function, so it would be just 10 over s. Rearranging our equation would be xs. I have 10, this would be 0, so we'll have this s and 2s plus 1. If I use the final value theorem for part A, I can find the steady state response. We don't have to use the final value theorem. We can find the overall response and then set it to infinity to see what would be the value. But here, if I want to find a steady state, would be 10. I have s 2s plus 1. Remember that this s appears when we use the final value theorem. So I can cross these out. If I s goes to 0, the steady state response would be 10. To find the time constant, I need to use fraction expansion equation. Here I have 10 s 2s plus 1 would be equal to as plus b 2s plus 1. I want to find this a and b. So here I have 2a plus b. That would meet the s coefficient. In the numerator I don't have any s, so that would be 0. And then I have a as 10. So plugging this here, b would be negative 2a or negative 20. So my xs would be 10 over s negative 20 2s plus 1. Change it to xt. 10 over s would be 10. And then here I can divide everything by 2. So call this 10, call this 1, call this 1 over 2. So they gave me negative 10 e minus t over 2. Or I can factor this. Looking at this, my time constant would be 2 seconds. I just compare it with t over tau, and here would be 2 seconds. To eliminate 98% of the difference between initial condition and a steady state, I have to be at 4 tau. So that means that t 8 seconds. After 8 seconds, I will reach 98% of steady state. So for our case, the steady state is 10. So 98% of 10 would be 9.8. So almost after 8 seconds, we would reach at 9.8. Let's look at part B or part C of this problem. We want to repeat this, but with a different initial condition. This time the initial condition is not 0, it's 5. We want to know whether changing the initial condition would change the steady state or the time constant. So let's repeat the problem. Here we have 2s xs minus x naught, which is 5 here, plus xs equals 10 over s. X naught is 5. Rearranging everything would be 2s xs minus 10 plus xs equals 10 over s. Factor xs, because that's the response, that's what we want to find out, would be 10 over s plus 10. Again, xs, you would have 10 plus 10s, and s 2s plus 1. If I use the fraction expansion to make it simpler for myself, 2s plus 1, I need to find a and b, so that'll be 2a plus b would be 10, the coefficient of s, and also a here would be 10. So in that case, it would be 20, b would be negative 10. Now I can have my function xs as 10s plus negative 10, 2s plus 1, finding xt would be 10 for Laplace inverse, and again I can divide everything by 2. The numerator would be negative 5, here would be 1 over 2, and then here would be simply 1. It makes it easier for me. That would be negative 5e minus t over 2. So you can see the time constant still would be 2 seconds when I compare it to t over tau. And the steady state, if the time goes to infinity, this component would be 0. So x steady state would be 10 minus 0 would be 10. So it did not change the time constants or the steady state. So you can see that changing the initial condition will not change the behavior of our system. Let's repeat this time with changing the initial condition, but also changing the input. Changing the input will not change the time response or the time constant, but it will change our output, our steady state response. But let's find that out. Again, let's write our function here so remember which function we are dealing with. 2s xs plus xs equals 10. I had 10 here, but this is 20 over s. So my xs simply would be 200 s 2s plus 1. If I use as plus b, 2s plus 1, 2a plus b would be 0. That's the coefficient of s, and a would be 200. That gives me b to be negative 400. So for my xs function, I have 200 minus 200s minus 400 2s plus 1. Similar approach, I have 200 minus 200 e minus t over 2. So the steady state response will change, but not the time constant. So tau would be 2 seconds. The steady state response would be 200. Simply, if you have t goes to infinity, you will find out that xt would be 200. We could also use final value theorem to find the response of the system, the steady state response of the system when we had this value. So we can conclude the input or the initial condition does not change the time constant. That's the behavior of the system. The initial condition does not change the steady state response, but having a different input will change the steady state response.